Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for September 5th, 2012.
On this week's show, a mix of X-rays and optical waves probe light at the atomic scale, lasers for standoff sensing are improved, and two new methods significantly improve microscopy speed and resolution.
An international team led by Lawrence Berkeley National Lab successfully probed the effects of light at the atomic scale by mixing X-ray and optical light waves at the LINAC Coherent Light Source at the SLAC National Accelerator Lab. Direct measurement of how light manipulates matter on the atomic scale has never been possible until now. The team used the LCLS to mix a pulse of super bright X-rays with a pulse of lower frequency laser light. By aiming the combined pulses at a diamond sample, they could measure the optical manipulation of chemical bonds on the crystal directly, on the scale of individual atoms. X-ray and optical wave mixing provides information that conventional diffraction cannot, such as direct information on how the valence of electrons respond to light. Because mixing X-ray and optical light waves creates a new beam, which shows up as a slightly higher energy peak on a graph of X-ray diffraction, the process is called sum frequency generation. But sum frequency generation requires intense X-ray sources unavailable until recently. SLAC's LCLS is a free electron laser that produces the needed ultra-short pulses of high-energy hard X-rays. The work appeared in Nature.
A new resonator design that controls both wavelength and beam quality enables the purest, brightest, and most powerful beams ever from a single-mode infrared quantum cascade laser. The work improves the accuracy of the lasers, critical for boosting the standoff detection of gas, explosives, or other hazardous materials to even greater distances. Almost all chemicals, including nerve gases and toxic industrial materials, can be identified by infrared absorption in the 8 to 12 micron range. Successful standoff sensing applications require a high-power, single-mode laser source with exceptional beam quality. Incorporating all three qualities into a single device has presented a significant challenge, and many complex structures have been proposed with limited success. But the Northwestern University group of Manija Rezegi developed a resonator using a new type of distributed feedback mechanism called b-dfb, a simple diffractive feedback in an angled laser cavity. Rezegi and her group demonstrated greater than 6-watt peak power with nearly diffraction-limited beam quality at a 10.4 micron wavelength, the highest power single-mode semiconductor laser demonstrated at a wavelength greater than 10 microns. Greater output power is expected with further refinement, particularly in the optimization of the cavity design and the gain medium. Rezegi says the resonator is promising for creating inexpensive, high-power, single-mode laser sources with good beam quality and can be realized at room temperature, and the design can be applied to a wide range of semiconductor lasers at any wavelength. The findings appeared in Applied Physics Letters.
A technology used in projectors can create a high-resolution image 100 times faster than conventional microscopy equipment, which can be too slow to clearly document speedy biological processes. The Confocal microscope, developed at the University of Leicester, addresses the need for rapid scanning microscopes with no loss in image quality. It bolts onto a regular microscope and projects light patterns through a system of mirrors onto the sample. Only light that is precisely in the plane of focus returns along the same path and is reflected by the mirror onto a camera to form an image. By programming the mirror device, the researchers can easily adjust the illumination pattern for different types of specimens and conditions. The microscope also takes out unwanted light that comes from out-of-focus specimen regions, improving image quality. The images produced can be scanned onto a computer at about 100 frames per second, showing biological processes such as cell activity at higher speeds than conventional devices, which typically scan around 1 frame per second. The technology will be helpful in biomedical research and neuroscience, as well as other fields that require optical detection of biological events as they occur.
In other microscopy news, researchers at 6 Italian agencies have built a system that is 100% sharper than conventional light sheet-based microscopy methods. The new method integrates light sheet microscopy and confocal microscopy, and it's called, appropriately, confocal light sheet microscopy, or CLSM. It allows high-speed, single-plane images of multiple sections of a sample to be taken with high-contrast fluorescence while also eliminating the scattered background light that causes blurriness. It proves superior to conventional LSM when used to view 3 samples of the mouse brain: the hippocampus, the cerebellum, and the whole brain. CLSM was also used to map the network of large neurons found in the mouse cerebellum and to trace an entire brain's neuronal projections. This is the first time that a fluorescent mouse brain has been imaged in its entirety with such clarity. In principle, the technique could also be extended to the human brain, but first the problem of staining fixed tissue fluorescently needs to be addressed. The team believes the technique can move beyond brain imaging and is ideally suited to explore the anatomy of different specimens such as flies and embryos. The work appeared in Optics Express.
That's it for this edition of Light Matters, Photonics Media's weekly newscast. We'd like to hear from you. Tell us what you like or don't like about our program, and also any topics you'd like to see us cover. We welcome your comments and suggestions at lightmatters@photonics.com.
You'll find links to share and subscribe to Light Matters by clicking the Share with Friends button on our video player.
Thanks for watching, and we'll see you next week.